participants. Thank you all for being here. This is very exciting. We have our guest today is Aziz Zaroui, and he is a teacher in Churchland High School in Portsmouth, Virginia. He's also a NASA ModSim Teacher Ambassador and a Math Modeling Hub Fellow, and recently a recipient of the Presidential Award for Excellence in Math and Science Teaching. Congratulations, Aziz. That's quite an accomplishment. And it's going to be great. He's going to talk to us about increasing student engagement using math modeling and drones in the math classroom. And as we go along, we invite you to type in your questions in the chat or your comments. I'll be monitoring for that. I'll be monitoring that for Aziz, so that if we want to stop him and have actually ask the question, he said it was okay for us to do that. And then also I want to remind you that we are recording this, so if you have colleagues who wanted to attend or you want to go back and have access to the recording, that will be posted on the mathmodels.org website at the COMAP website. And of course, we're thanking COMAP for sponsoring these webinars. And we'll kind of put a plug in for the next one, which is April the 21st. At 4 p.m. We'll have 3 high school teachers as part of a mathematics panel that will talk to us about how they engage students in math modeling, both using problems in their classrooms and also through the math modeling contests. So I'm going to turn it over to Aziz, and then if you have questions, feel free to raise your hand or just type things in the chat. So thank you, Aziz, for being here.
All right, thank you. Thank you, Maria. Welcome everybody, and thank you for joining me today. And so this is basically me sharing an experience that I've had. I am a math teacher. Currently, my assignments is geometry and AP calculus, so I'm still in the classroom. So this is an experience of mine, the good, the bad, and the ugly. So, however it is, please, if you have any comments or questions, feel free to interject. Maria has graciously agreed to monitor the chat for me, so she'll be able to stop me and let me know about your question. So basically here, the inspiration for this particular lesson has come from somewhat of a frustration with some of the issues that the students have. No matter how much I describe certain situations or certain connections, the students just seem to lack the connection, even though, like, for example, we talked about trains or we talked about airplanes and stuff like that. It was just in the realm of the imaginary, and the kids just did not really connect with it as strongly as I had hoped. And so the thought was, is there a way that we can get something physical in class to actually engage the student and really kind of like get that attention, to grab the attention, and to somehow be almost impossible to lose that attention. And so I started playing with drones for a bit. And so it really started with me from, those are all drones that I have owned or still own at some point. I think this one right here, the big one, that you see over here, I still have it. Actually, it's right behind me over there. And that was one that I have, built myself through a workshop. This one here is the one that, pretty much everybody knows or really think about when you mention drones. That's the DJI drone, and it's really nice, although very, very, very expensive. That was just a loaner. I couldn't really afford that. And so this one right here is the Tello drone. And until, so this one here was too big to use in the classroom. So every time I wanted to use it, I had to, basically take my class out and stuff like that. It was too much of a hassle for me to do. So I pretty much just use it as a display. This one is nice, but then again, too expensive, couldn't really use it myself, and I am a terrible pilot, so it was not something that I was gonna borrow and then crash or something. So this one right here has been introduced to the US in like March 2018, and this is like a very small, if you look at the camera, it's actually right here. So it's really you know, small, but it's actually, it has all of the bells and whistles of the real big one, which is basically that it stabilizes when it flies. So you don't really have to worry about those you know, sudden moves that usually make the pilot panic. And so once I had that, I was like, okay, you can fly it indoor. It's very you know, easy to fly, stabilizes itself, hovers, you know, while you're trying to figure out what's going on. And so it was really a game changer when it came to the US. And so at that point in time, I started saying, okay, well, if I bring it to the, you know, to the classroom, what am I going to do with it? Well, I needed a problem to attach to it, and that was the problem was inspired by an actual engineer, or local engineer, and basically the problem being is that the drone itself has only 2 sensors. Yet when you read the data, you have 3 outputs. You have an output for height, an output for velocity, and then an output for acceleration. But the sensors, we only have a sensor for the height and a sensor for acceleration. So the question is, 1, how is the drone getting the velocity measurement? How is it outputting you know, that measurement? And then the second one is, and this was actually an exercise that that engineers do. Before you send, you know, thinking of, for example, an expensive drone, before you send it, you need to verify that the sensors that you have on board actually work. You know, if we consider, for example, that the Mars rover, the Perseverance that just landed, I think, in the last couple of weeks, you know, you want to know that the sensors that you put on board are actually going to work. They're not just going to go there and then nothing happens. And so here, how can we verify that the height is actually giving us the right output, and then also that the measurements of acceleration are also giving us the right you know, output? And so that right there basically lended itself into a very nice you know, calculus lesson. Okay. At this point in time, this was done sometime end of March. So at that point in time, the curriculum of AP Calculus has ended. So the kids that you will see actually know how to derive, know how to integrate, know you know, all computational methods, approximation methods like Riemann, some like average rate of change. And so they know that stuff. So at this point in time, it's more of an application. Can you connect what you know and try to explain what is happening? And so this is just an excerpt of what is going on, or this is actually the introduction of the lesson. And I think this was supposed to be a video, and it is not playing. All right, so no big deal. So I hope that you can see the drone is right there. Okay, kind of tiny thing. And as a matter of fact, as I was flying it, it kind of came a little bit to a small crash at the end, and you know, the kids got a kick out of it. But the idea is that was it immediately commended the room. It immediately, everybody was looking, okay, what is this? And so it was a very simple introduction. The drone had to fly up and down, and now let's explain. Let's collect the data and see what's going on. Now, the data that was collected was something looking like this right here. So as you can see, we have the height, we have the velocity, and we have the acceleration. And as you can see, the acceleration versus a corrected acceleration, just because of, you know, some of the units in there, we needed to do some corrections because you know, the sensors are too sensitive based on where you're flying this thing. You know, this is something that the kids have gotten just the way it is. And so right there, I kind of took the back seat, and I was thinking, you know what? Here it is. Now let's see what we know about the connection between position, which is the height, velocity, and acceleration. So velocity is the derivative of position, acceleration is the derivative of velocity, and then vice versa. The velocity is the integral of acceleration, and the height would be the integral of velocity, or, which was kind of like an interesting occurrence, many have referred in this particular situation to the height as a double integral of acceleration, which was interesting because in the past, I did have some students that would, you know, somewhat just do their searches, and then when they see a double integral, they just flip. In this situation, it happened organically into saying, okay, well, if I am not to rely on the velocity reading, because really I don't know where it came from, then I should probably just pay attention to the acceleration and position. And so the relationship would be that the position is a double integral of acceleration, and then the acceleration would be a second derivative or a double rate of change, you know, of the height. And again, these came from the students without me having to prompt them to anything. And so at this point in time, the other thing that happened here is that the kids now are starting to embrace the modeling you know, aspect of things, because they are looking at the data and they're getting overwhelmed. They're looking at the data and they're realizing that this is too much. This is too much data for us to handle, especially that they are thinking, okay, well, if I have data, how am I going to integrate the acceleration? Well, if you have just, you know, the numerical definition of the function, then you would have to integrate using Riemann sum. Well, first look, one look, 2 seconds, and then they came up with that. I'm not going to do a Riemann sum to all of this. This is way too much. I think we've had like, you know, this is cut. And this is something that I will have available. So, you know, after this webinar, if you guys come back, you will probably get an email notification of the availability of this. So this will be an Excel spreadsheet, and you can look at it and you can even use it. And I think we had like almost 140 data points, and it takes like one reading every 5 milliseconds. So it was massive. And at that point in time, the kids started talking, look, we need to clean this up. We need to have something. We need to do something to this data in order to make it look better, because again, I am thinking of having to do Riemann sum or doing the average rate of change, both of which are going to be, you know, a calculation nightmare, and I don't want to have to do a whole lot of that. And so they started kind of like brainstorming things, and one of the things they came up with, which is the let's maybe graph it and see if we're gonna create some kind of cloud of points to see where this is going. And so they did. And when they did, we came up with something like this. And then at this point in time, they realized that right over here is not really interesting. And then over here is kind of like, this is where the drone is actually coming down. And the drone is not very, when it comes down to land, is not very smooth. So it's kind of like bounces. And if you remember, I did say that it kind of like had a little crash. You know, nothing bad or anything, but you could see that at this point in time, something crazy, you know, happened there. And so in this situation right here, the blue points are the data that the sensor for acceleration is collecting. That's the blue data, okay? And what we're having here is the red data, or the red points, are actually the velocity that the drone is outputting. And right here is a moment to kind of like celebrate, because we're starting to see some things that are very impactful in calculus and specifically for the AP exam. And so we needed, again, a little bit more cleanup. And so we cleaned it up and we zoned in on just this little section right here. And so at this point in time, we are looking at what? We are looking at the red, which is the velocity, and then the blue, which is the acceleration. And so basically we are looking at the function and its derivative. Okay, so basically if we want to kind of like go a little bit more simplistic, we can go ahead and just call it by f and f prime. So this is f, the red is f, and then the blue is f prime. And as you can see that the lineup here, that where the maximum of my function happens, I do have that the derivative kind of assumes a 0, which is a critical point. And then before the critical point, we had the derivative being positive, which means that my function is increasing. After the critical point, I see that the function is, or the derivative is negative, which means that my function is decreasing. And so all of these are, you know, very huge topics, you know, for the AP calculus exam and for calculus in general. You know, if you are thinking about calculus, Calc 1, first year of college. And so we're starting to do this, and at that point in time, this is where the, you know, the role I played. The role I played was to monitor the conversation and to just kind of like nudge the kids into using the knowledge of calculus, into using mathematical language and notation to actually express what it is that's going on right here. So we also, for example, here with the velocity, we are thinking, okay, the velocity is positive. So velocity is positive. What is the drone doing when the velocity is positive? So, you know, the translation, the hope is that they will define that when the velocity is positive, that means the drone is actually going up, and that when, you know, the velocity hit, you know, a negative right here, that the drone was actually, you know, coming down or something like that. And so all of these conversations, basically, I just played the monitor, as you can see in the, you know, from the class, you know, picture. They were set in groups, and, you know, I was just going around eavesdropping and looking at things. and trying to probe all of that. And so here, for example, this is the actual height graph, the height graph versus an estimation of the graph. So this one right here, the blue, that's actually the reading of the sensor, of the height sensor. And the red is the approximation of the height from the acceleration sensor. So how did we approximate that? Well, basically, we had to double integrate. And how can we double integrate when we have numerical? Well, we had to do a double Riemann sum. And if you want to do double Riemann sum, you better not work with 140 data points. You had to actually clean it, correct it, and kind of like bunch them up. So we kind of like took readings every maybe 1 second, every 2 seconds, and we averaged what was happening within 1 second, and we looked at that as being one number. And at that point in time, again, organically, without me having to say, well, no, we have to think about this, we have to think about that, we started getting a bit of certain differences in answers. And so the kids, being part of the same group, they're providing, giving two people to do the Riemann sum, and they're not getting necessarily the same numbers. Between groups, they're not getting the same numbers. And then we started talking about some of the assumptions. The assumptions being, well, for me, I took 5 data points versus somebody else who took 10 data points. Well, 10 data points, they agreed that that would be a lot more accurate. And so right now we started to talk about accuracy. Okay, well, if you start talking about accuracy, then we are thinking of that there is some kind of inherent error with our answers no matter what. And so right there, they looked at these as being a great result. Why? Because, again, they look the same. They might not be on top of each other, but then we attribute that into our errors here and there. But we took that as a win, because technically right now, I used the acceleration reading and it confirmed the reading, the true reading from the height sensor. And so again, they are getting to this without me having, to say anything. And they are kind of like really connecting with this idea to really realize that, okay, the mathematics that we have learned so far actually can describe and can solve the issue that we have posed at the very beginning. So this is one of, just the same thing, but we kind of like pushed it a little bit further and we cleaned it even more. And as you can see, when it's cleaned up, look at the side right here, we have maybe like 22 data points, and we have kind of like a real nice collection of points there. And then there is a graph, there is a function that fits this pretty nicely. And so at that point in time, we are starting to kind of look at the data that was in a table has now become a model, has now become a function. And again, I mean, I'm so excited about this, but then sometimes I'm sure I'm preaching to the choir here, but you say it so many times during the year, and then all of a sudden they look at you and say, oh, this is what you meant. And so it was interesting that they have arrived to that particular conclusion by themselves. And that is that you actually started with the data point. Because you did not have a model, you had to use computational methods. And computational methods are what for us? They're basically the Riemann sum, the average or the difference quotient to do the derivative, and then the Riemann sum to do the integral. And then at one point, you really don't want to keep using computational methods. Why? Because we have errors, it's too much work. And then of course, we would like to have some aspect of prediction involved. And at that point in time, the function that came was like, oh, I could use this to kind of like guess what the behavior would be later on and stuff like that. And so that was, again, a key moment for us. And then thinking about the AP Calculus exam, they have many questions where, on the field response side of things, there is the first part is numerical, computational methods. You can't do anything. And then the second part, they create the model. And then all of a sudden, it's all about the model. Forget, the numerical definition. And the kids usually have a huge problem with that disconnect. And so now we're realizing, look, at the beginning, you were talking about approximations because you didn't have a model. Now that you have a model, you need to focus on that. So of course, with this, I had to kind of, as you saw at the beginning, the kids were, many of them, or I had many groups, so I couldn't really be everywhere at the same time. So I created kind of like a student guide, to kind of like just tell them, hey, well, what's going on? Well, what do you think is happening here? What do you think is happening there? So this is just kind of like a small picture of the beginning. I couldn't really fit it into one slide. And so the idea here is to get the student going without me having to be there. And so that really allowed me to go into, other groups and have kind of like a one-on-one conversation. And by the time I'm done with that, they're actually, going, not just waiting for me. This also allowed a little bit of a differentiation because I did have a group of students that were going for BC. And for that particular group, the questions or the conversations went into, okay, well, there's an error. Okay, what is the magnitude of that error? Versus when you are talking about Calc 1 or you're talking about Calculus AB, you're just talking about acknowledging that you have an error and then basically maybe over under. But for Calc 2 or BC, we do want to know how much of an error that is, or the magnitude of the error that we have. So this companion, allowed me that bit of freedom to have the kids, work by themselves and then kind of, check with me, or of course me just basically walking around and breathing down their neck. And so, you will have all of the resources that I'm showing here, you will have access to later on. And, what I mentioned about the data, you will have access to that data. So if you, like this particular activity, you can run it without having to have the drone. There's the issue of cost. Although this one right here is relatively cheaper than what you would see. I think I just checked it a couple of hours ago, and I could find one at Amazon for about $99. The whole package, which gives you like few batteries and stuff like that, is about like $149. I mean, It's cheaper, but again, for a teacher, it's not cheap. My school has graciously, agreed to buy, and we bought two, just to have the issue of one, of them breaking down, and it seems like there is an issue with that particular feature of the drone. The batteries usually just kind of, if they stay without operation for a while, they break. And so before we did all of this, I gave a pre-test, basically. I just wanted to see, something like some measurable data to see, okay, that does include in, math modeling, or pushing the math modeling in the classroom. Does it actually yield the results? And so what I did is I took this particular question, and this is a question that was adapted from the 2015 AP Calculus exam. This is question number 3. I think it was a something about Joanna is jogging, and so I basically just took that and modified it and started talking about a drone. These numbers right here they're okay, in a sense that they are on the slow side for a drone, but usually if you're flying a drone, you're not really gonna push it to be crazy. So here, 8 miles or 8 meters per second, that's about 18 miles per hour. Drones that we have, in the market are anywhere between 50 and 70 miles per hour. And I was involved in a, drone racing camp, and those, they were going like 87 miles per hour. And if you don't watch yourself, I mean, you can really do some damage. So we're not trying to do that. We're just kind of like thinking about like, some beginner trying to fly. And so I basically this is the formatting of what an AP Calculus exam question would look like. But the material is completely me. The data is me. I even used, why not? These are names of my students that were in that group, Kiani and Malik. And that is, introducing some culturally responsiveness strategies, to include the names and stuff like that. The kids did get a kick of that. And so this, you see this function right here, I actually got that from this data right here. Okay, and so I just kind of like made it sound like it was completely different, but it's actually this one right here. And the way you do that is basically you just get it. I use GeoGebra. I'm partial to GeoGebra. Many people like Desmos. No disrespect there. I just like GeoGebra better. And so that right there, basically, it's, as you can see here, it's not really a very good fit, but, we kind of like went with it. And so, from there, I gave them a, this is the scoring guide right here. And again, the scoring guide is made out of, to mimic what a scoring guide would look for the AP exam. But again, the numbers and everything are entirely, my numbers that I got from the actual, drone. Okay, and so this one right here, I usually kind of, let the kids, play grading each other's papers and stuff like that. But on this one here, I did look at the papers, got the data before I gave it to everybody else. And so at this point in time, once the lesson has been given and the activity is gone and stuff like that, I did put a post-test. But before I talk about the post-test, I want to talk about what worked And so in this particular situation here, what worked is, bring in the drone. That thing, as small as it is noisy. So it commands presence. I mean, you cannot really ignore it. The engineering problem, the fact that it's not my problem. So they look at me and say, hey, I don't know. You guys need to, this is what the problem is. And it came from an engineer that works with the drones, that has those, problems, that asks these kinds of problems constantly. And then, of course, here, the conversations of the students were actually spot on. They were, they embraced that whole F prime, F second. They embraced the, approximation aspect, the error aspect. So all of these kind of worked in our favor. And so, after this, I did give a post test. And as you can see here, the data, this is the data from the post test. And so what I did was, obviously, I don't know, I mean, there is an argument towards having the same pre-test and post-test. But for me, I did not do that. What I did is, the pre-test was my questions that I adapted, that I changed. The post-test was the actual AP exam question that was graded using the rubric from the the College Board. And so here you can see that there is a somewhat I thought it was respectable gain, even though, for example, for this one here, we still had, some people that were struggling, but you can see that the substandard column has been kind of enlightened a little bit. So from 10 to 1, from 12 to 3, from 15 to 6. And so I think that if we had given it a little bit more time, we might have gotten a little bit further with this, but those were just the aspects that I could measure. They were clear at the beginning and they were clear in the post-test. And so I could actually make the comparison between what was and then what it is afterwards. And obviously, like any other lesson, a whole bunch of stuff didn't work. And so what did not work? So for me, a lot of kind of like the logistics here was kind of like an issue. And then I found out, like, while I was doing the lesson, so I couldn't really do anything about it. So for one, the companion, although was helpful, was not as specific as I would have liked. So I did modify certain things, but if you are using this activity, I really I would suggest for you to tighten it up, just to be a little bit more specific about what you want the kids to have. At this, right when I did the lesson, again, the technology was not such that I could do anything. And so what I did was I got the data and then I pushed it to the students through Google Classroom. And the problem that happened with that is that the kids, so I have a question here. Did I attach the sensors? No, the drone has 2 sensors, and that's the height and the acceleration. So I did not really attach anything. I would actually stay away from attaching, because usually that does interfere with the flight of the drone. And so, like I said here, the kids kind of gotten ahead of me, and so they got the data while I was still building to that. And that was kind of something that I did not really like, although I kind of like ran with it. And then because they got the raw data, it was just, the file was massive. And then when the graph that got generated from this data was just really tiny, you could still see the patterns and stuff like that, but it could have been better. And as you can see from what I showed you, we did a lot of zoom in, zoom in, zoom in before we got to one that was kind of like, oh, that's interesting there. So, although, all of this seems like a lot of problems and stuff like that, well, believe it or not, it was actually a whole lot better than when the technology got improved. The Tello is actually able to connect to the Wi-Fi, and you are able to just kind of like sit it on the desk. You run it from your computer anytime that you want and stuff like that. Well, when I wanted to upgrade to that, the bureaucracy, the IT pushback from the building was just like unprecedented, and they just could not. It was a categorical no, not a no. Let's talk about it. No, we're not going to allow kind of like this little thing that has no security whatsoever to tag onto our network, because it's going to make us vulnerable and stuff like that. And so almost as much as the technology has advanced and we can do this particular activity a whole lot easier, to me, because again, like any other teacher, I really do not want when things kind of like get out of my control, especially go outside of the classroom. And so I would actually run it the same way, maybe with a little bit tightening of, do a time release on the data so that it's released right when I want it to be released or something like that. But, the technology has made things better, but the bureaucracy just made it impossible for us to embrace that. And in me looking at ways to kind of like, well, could I, circumvent this and stuff like that, I came across this particular, software right here. It's called the Tracker, and it's available through, I think Fizlit.org or something like that. I will have the link in the resources that we will have available for you after the webinar. And then, so this one right here was actually very interesting, because it can give you the data based on the movement of an object in a recording. So this is an example of me running this. So this is kind of like this is a parachute. And right there, you see those red dots right there? That's actually the tracker picking up the data and populating this table right here. And as you can see, you have the table, you have a graph, and the graph, there's like so many different options that you can run. You could do acceleration with time, you could do height with time, you could do velocity with time, and it has an analyzer that can actually, also fit certain things that you can do with the data. You see it right there? You can fit a line, you can fit exponential, and at this point in time, conceptually speaking, I have the idea, but I cannot say that I have run this. But this is kind of like how can I say that? Like a halfway compromise between me having to, to go against the powers that be. And so I can actually just run the experiment, record it, maybe track it, and kind of get the data. And then once you have the data, once you have the model, it's not just specific to calculus. It could be, anything. Pre-calculus, definitely. I don't know which state you guys are in, but we have a class here called Algebra, Function, and Data Analysis. This would fit beautifully in there. And so I think I am almost at my time. So if you guys have any questions, please don't hesitate.
Thank you, Aziz. If you all have questions, you feel free to type those in the chat, or there are few enough of us, I might be able to unmute you as well if you'd like to talk. So we'll wait to see if anybody has any questions or comments. Here we go. Ingrid says the tracker is interesting and looks like one weather stations would use when they
send balloons up.
Send balloons up. Yeah.
Yes, the tracker is interesting, but one of the things that I would say is if you use the tracker, make sure that you have a good contrast between your object and the surrounding environment, because it does, look up colors. So for me, I did have some problems because I used like a white capsule, and then my walls were kind of white. So I had to kind of like track it by hand. And this is one of the very few, systems or softwares out there that if you have a question, you ask the question, and then the creator of the software answers you. So that was kind of like, I got a kick out of asking a question and then him answering me. It was cool.
And then there's another question. Did you use a vertical path for your drone flight?
Yes, and that is actually, I try to be fancy saying a vertical path, but that's what a GPS column is. GPS column, that means you actually look at the drone, and it's a term that is used professionally for drones, is that you just fly it up and down until it locks on a GPS. So you don't just come in and fly it. You have to kind of like fly it up and down until it has a good GPS lock, and then you let it go so that you can have it back. We all, hear about those accidents where it just goes and never comes back. And so, yes, the GPS column is a vertical up and down. The Tello drone, actually, because you're not actually flying it, there is a system that's flying it for you. So for you, you just say up and how much, and then it goes up, down, and it has a possibility of doing a flip. You can just right there and you tell it to flip, and it flips. Now, again, it gets points for cool effect, but the problem with that is it's just gonna give you some horrendous data if you do that. And so if I am flying something like that, I would definitely not try to do those acrobatics, because again, you'll pay for it when you see the data.
Any other questions? I've used Logger Pro before, and that's kind of a pay-for version of the tracker to import videos too. And that's nice because you can grab data right off the video, like you could have a ball bouncing or something like that. So there are a lot of nice data collection tools out there now.
So absolutely, with the tracker, it's kind of like one of those things. If you are unable to use the drones in class, you can fly it at home and then kind of like do all kinds of analysis, get the data, and then show it in class. As a matter of fact, even when it comes to the AP exam, there is always this particular question that says, here's the data, describe the movement of the drone, or describe the movement of the particle, describe the movement of the object. So as much as we would like for the students to see the movement of the drone, there is some aspect there that at some point we would have to say, okay, now could you describe what the drone was doing just by looking at the data? And of course, they would see, for example, if the velocity is negative, that the drone was coming down, the velocity is positive, coming up, something like that. And so that whole idea of doing the experiment a day ahead is not necessarily a bad idea or inauthentic. I would actually, moving forward, I would think a lot harder at doing the experiment ahead of time. Yes, absolutely. I mean, a horizontal, if you are talking about a horizontal path, it is the exact same thing as it's like an inverted or a flattened vertical path. So it is, for all analysis purposes, it is the same thing, except that instead of an up and down, it will become left and right. So that would be the only difference that I would see there. If you are, kind of like looking at some devices out there, I think the TI has the rover. It's actually it's a rover. It's a little car that keeps going up and down, and for that one right there, you could basically do the same thing. I could even almost venture this, which is the sensors that are on the drone. You could just sit the drone on top of the rover and then run it, and the sensors will pick up those readings, except that the height is not really going to be interesting because you're sitting at the same place. Okay, so I actually kind of like got on that without seeing your question. So theoretically speaking, and I was actually contemplating that. The answer is yes. Of course, it will depend on what accelerometer you're using. What I was thinking is basically use the accelerometer that's in this Tello drone, to give you that data. If you remember, that very that very first slide, I think I want to see if I can get back to that. That big drone that I have right there. So that very first drone. So this one here, this was my very first drone. That one right there is packed with sensors. And so yes, I could fly it. I could put an accelerometer. I could put a light sensor. I could put all kinds of things, and it's big enough to where it can handle that. The Tello is too small to handle load, but although it can actually get some load on there.
Aziz, I'm going to read these other questions just so we'll have them in the video as well. So it says, so most drones are able to collect this data, vertical, horizontal, acceleration, question mark. Can you tell I don't know anything about drones?
Believe me, when I started with this, I did not know anything about, and I'm telling you, this particular drone, you really don't need to know anything. It flies very nicely, flies off of your phone. The whole issue is, how do I collect the data so that the kids can get to work? That becomes the main issue. And I'm pretty sure that a lot of people out there can actually find a nicer way than I did to collect that data.
And then after, this says, after we break our drone, we could salvage the accelerometer.
Good luck with that. I mean, I really don't think, I mean, these things are like so small on the inside. I doubt that they would have, that you would be able to salvage it. But I think the one thing I learned from building my own drone is that everything can be sold separate. So, and it's not really, you don't have to look too far. You can actually just go to Amazon, and then you can have all kinds of little, sensor here, sensor there. Of course, price is an issue. For example, this particular thing, the reason why I abandoned this project is that you need to be a good pilot to fly this thing. And why? Because it was not equipped with a GPS. And why did we not equip it with the GPS? A GPS was too expensive. It was like $57, and this is 3 or 4 years ago. So we were not, I mean, it's built out of styrofoam. I'm not gonna put $50 on a GPS. So we had, and we tried to kind of like say, well, okay, there's a lot of mathematics in there by trying to stabilize logically. So how do you do that? By photosensitivity. There's like a small camera. The camera costs like $8, and you can take pictures, and then you could, you know, study the differential, and then somehow the drone would recognize where it's at. Unfortunately, it was not very, you know, successful, and part because we were in we were in a school building, and the floors were uniform. So if you take a picture of the same floor, the drone had like a really hard time telling the difference that it's even moving. So it would hit a wall and not even recognize that it was moving.
Okay, so there are a couple of questions, and we don't have very much time, but Ingrid has said, how can we keep the conversation going, which is a great question. So Aziz will have his email on, I think he has it on his first slide, or maybe his last slide. We're going to post the PowerPoint in the mathmodels.org website, where we'll also post a recording. So you can send him emails and keep the conversation going. And there's another comment about thinking about how all the phones now have all these sensors. Might be an interesting project for students to explore that. So again, in the interest of time, I want to make sure that we honor that. Maybe you guys could keep the conversation going. Thank you very much for attending. And thank you, Aziz, for your presentation. Wonderful to have you here. And I hope you guys will join us in April 21st at 4 p.m. We'll have a panelist of 3 high school teachers who will be talking about how they engage their students with mathematical modeling. And then we'll have one more in May. We haven't set the date for that one yet, but that one is actually going to be focused on middle school. So if you have colleagues who teach middle school, there'll be an announcement for that one coming, because we really want to think about how we can engage students in middle school as well as high school or college, university level. And in particular, the HiMCM, which is the COMAP modeling contest that happens every year in November, is going to have a middle school question on it. So we're trying to encourage folks to help kids kind of get their feet wet with mathematical modeling in the middle school. So again, thank you, Aziz, very much. And thank you all very much for attending. If you have any questions, you can send Aziz an email, or my name is Maria Hernandez. I forgot to introduce myself. I'm the facilitator for these. And I'm always happy to answer questions too. So thank you all very much. Have a wonderful evening.
Thank you, guys. Thank you for having me.
Yes, indeedy.